This video will show you how to measure steady-state and time-dependent upconversion luminescence spectra on the Edinburgh FLS980 spectrometer at the Molecular Foundry. This tutorial is intended for first-time users that are being trained on the instrument at the Foundry. The idea is that you would follow along with the video while you're sitting at the instrument performing your own measurements. While the operations here are specific to the Foundry, these instructions may be useful for users of other Edinburgh FLS spectrometers. The Edinburgh FLS980 spectrometer is an instrument for measuring steady-state and time-dependent luminescence spectra. It has double excitation and emission monochrometers and a variety of excitation and detection schemes. It has both visible and near-infrared detectors that can span the range of 200 to 1700 nanometers. It has a variety of detection modes, including steady-state luminescence, time-correlated single photon counting for nanosecond lifetimes, and also multi-channel scaling for microsecond and millisecond lifetimes. Luminescence can be excited using steady-state and flash xenon lamps, where the wavelength is selected by the excitation monochrometers. Or you can use picosecond pulsed laser diodes to perform time-correlated single photon counting. You can also excite samples with high-powered near-infrared lasers available at 800 nanometers and 980 nanometers. These infrared lasers can operate in both continuous wave mode and also with nanosecond pulses, which we use for microsecond and millisecond lifetimes. This video will focus on using near-infrared lasers for upconversion luminescence measurements. So we'll cover today turning the system on, running steady-state emission experiments, measuring microsecond lifetimes using multi-channel scaling, shutting down the instrument, and troubleshooting. Chapter 1. Starting up the spectrometer. The first thing you want to do when you first get to the instrument is to turn on the pH1 switch, which turns on the power for the spectrometer. Next, you'll turn on the CO1 switch, which turns on the power for the PMT. It will take about 30 minutes for the PMT temperature to stabilize below -21 degrees Celsius, but the longer you can wait, the less noise you'll have in your detector. So you should always plan to wait at least 30 minutes before you start doing your experiments. Since we're using the near-infrared lasers for this tutorial, we want to make sure that the desired laser is connected. The 980 nanometer laser is connected by default, so if you need to use the 800 nanometer laser, ask a super user. It's really important that you don't try to change these lasers yourself. These are high-powered lasers that have many different safety requirements. Only super users with the appropriate laser safety training are allowed to reconfigure and align lasers. Eye exposure to class 4 lasers is a major safety hazard. Bypassing these safety protocols can result in removal of instrument privileges. If you're using the near-infrared lasers, then you want to check the back of the power supplies to make sure the electrical connections are connected correctly. First, you want to plug in the BNC cable for triggering the laser, so the 980 nanometer laser is on top and the 800 nanometer laser is on the bottom. If this trigger is not connected properly, then the lasers will not pulse when you operate them for lifetime measurements. You also want to make sure that the interlock cable is plugged in the correct laser. If the interlock is broken, then the laser will not turn on. If you're using the near-infrared lasers for lifetime measurements or pulsing, you also need to unplug the trigger cable for the microsecond flash lamp. This is because the near-infrared lasers won't work if the BNC cable is plugged into the flash lamp. There's two separate triggering cables, one for the laser and one for the flash lamp, and you cannot have the flash lamp cable plugged into the flash lamp when you're performing pulsed laser experiments. Next, we need to insert a prism into the sample chamber in order to steer the near-infrared laser beam into the sample holder. The prism is located on a flip mount, and you can grab this flip mount using a rod. You shouldn't actually grab the prism since it's an optical component. So when you flip this flip mount down, the the prism will bottom out and then be horizontal with the floor of the sample chamber. This is a picture of the prism that's in place. You can see that now the laser, which comes from the side, will be steered into this solid sample holder. And here's an overhead view of the prism. And you can also see that we need to block out the laser beam so that it doesn't go right into the picosecond laser diodes. So we're going to install a beam block in the path of the laser after it goes through the sample holder. So here's how the beam block looks schematically in this 3D view. And this is a picture of the beam block both on a mount and also unmounted. So in the solid sample holder, you're going to place the mounted beam block here to the right of the solid sample holder past the focusing lens. If you're using a liquid sample, then it's probably easier to place the beam block directly on the filter mount of the cuvette holder. So you would use the unmounted beam block here. Optionally, you can also insert an excitation or an emission filter. So an emission filter is most common when doing upconversion since you want to block the very intense scattering from the near-infrared laser. So typically, if I'm using a 980 nanometer excitation, then I might use a 750 short pass filter or some other filter that allows me to have a broad transmission in the visible. A wide variety of interference and colored glass filters are located in the cabinet below the Edinburgh spectrometer. You should ask a super user for permission to access these filters. For the circular filters like Semrock 25mm filters, they need to be mounted inside of a Thorlabs cage cube mount. This can be a little tricky because these cage cube mounts weren't meant to be used with the Edinburgh filter holders that are shown in this slot. You should ask a super user how to fix the cage cube mount onto the Edinburgh filter holder. You may also need an excitation filter to clean up your laser. There's no set slot or Edinburgh filter holder for this laser, and so you can put a Semrock filter mounted in a Thorlabs cage cube mount either right next to the prism or mounted in a standalone Thorlabs mount right in front of the prism. Next, we'll turn on the laser. If we're using the 980 nanometer laser, we'll turn on the power supply switch shown here. The 800 nanometer laser, again, is the power supply located below the 980 nanometer laser. When you're ready to measure your samples, so not right now, you'll turn the key to turn on the laser. Also at that time, you can turn the knob to adjust the current, which adjusts the laser power. You can ask a super user for the latest calibration curve that correlates the current to the power. You'll also want to set the infrared laser to continuous wave mode in this dongle connected to the laser box. You'll flip the switch to CW mode or continuous wave mode. Next, you'll open the F980 software, whose icon sits on the desktop of the Windows computer that's located on top of the Edinburgh instrument. When you double-click this icon, it'll open up this F980 splash screen, and you'll see various messages telling you which parts of the spectrometer are initializing. Chapter 2, Acquiring Steady-State Upconversion Luminescence Spectra. So now we're ready to measure spectra of our samples. So we need to load our samples into the sample holder. First, we're going to make sure the laser is off. Then we'll open the sample chamber cover shown here. If you're using liquid samples, install the cuvette holder and mount the beam block onto the filter holder slot of the cuvette holder. If you're using solid samples, you need to install this angled solid sample holder. Next, you'll attach the translation rod into this moving stage into the front panel of the sample chamber. So the knob is used to rotate the translation rod and then move the solid sample holder back and forth so that it can translate across the beam. This is a little tricky, so you can lift up this panel up and away so that you can reach into the sample chamber a little easier. It's still tricky, so look at the video for how I do this. After you do this, you can replace the panel and close the sample chamber. The solid sample holder has a second piece that's a clip that can clip onto a glass slide or a cover slip. You can see me clipping in this cover slip that has my dried sample into the clip assembly, and then I can slide this clip into the angled solid sample holder base. So once I can do that, I'll close up the sample chamber. So now we're ready to set the software settings. When you opened up the F980 software, it should have automatically opened up the signal rate window. But if you don't see it, you can click this icon in the leftmost side of the toolbar. It looks like 3 different bars. The signal rate window is really important because it gives you a live measurement of the intensity of light measured by the detector. In order for this to be a useful measurement, we need to actually set up the spectrometer correctly. So first we'll set the light source path. Here we're going to set it to XE1 for the steady state spectrum. So this stands for the xenon lamp, but it also applies to the near infrared lasers in steady state mode. For other modes such as MCS or TCSPC, you would choose the options with those particular labels. Next, we'll set the grading. So here you'll choose the grading with the label that corresponds to the wavelength that's closest to your peak emission wavelength. If you're using a lamp, you would set the excitation wavelength and the bandwidth. Here you'll set the emission wavelength to the wavelength of the peak of interest. You'll also set the emission bandwidth to 0.1 nanometers. This sets the slits, and right now we're going to close the slits down as small as possible to avoid saturating the detector. Next, we'll turn on the near-infrared laser power supply if it's not already on. You'll turn on the power supply, turn the key to actually activate the laser light, and then adjust the knob to your desired power. Again, the laser should not be on when you're not using it. Once the laser is on, you should see that this emission 1 signal should have increased because you're getting luminescence or fluorescence from your sample. Ideally, this signal should be anywhere between 10 to the 5th to 10 to the 6th counts per second. Anything higher than that is bad because you're saturating your detector, which is the PMT in this case. So if the signal is too high or too low, you can adjust the emission slits. If you increase the bandwidth, then you'll get more signal, but at the expense of having worse resolution. So in general, it's good to aim for a bandwidth of about 1 nanometers for most general spectroscopy. Anything higher than that will broaden your peaks, which may not matter to you if your peaks are very broad anyway, but if you're looking for fine spectral features, then you would want to keep the bandwidth to about 1 nanometers or less. There's a couple other ways you can optimize the emission 1 signal. If your signal is too high, you can install a neutral density filter in the excitation or emission beam paths. You can also adjust the position of the solid sample holder by turning the translation knob. This will change both where the laser is focusing on your sample and how it reflects into the emission monochromator. So finally, you're going to exit the signal rate window. You can click Apply and then close the window. To actually set up an emission scan, you can click on this lambda button, and then you can set the start and ending wavelengths for your spectrum, along with the step size in nanometers. Next, you'll set the dwell time or the integration time at each wavelength step. You should set this somewhere between 0.1 and 0.3 seconds. Anything longer than that doesn't really increase your signal to noise. To increase the signal to noise ratio, it's actually better to increase the number of scans. Click on the Correction tab to set the spectral correction parameters. Here it's recommended that you check the Subtract Background box. This baselines the signal to a dark reference. For the infrared lasers, you don't want to check the Correct By box in the excitation correction subwindow. This is only used for lamps. It is recommended to check the emission 1 file in the emission correction box. This corrects for the different sensitivities of the PMT detector to different wavelengths. It's not a big deal if you don't check this box because you can always correct your spectrum later. It is important to choose the subtract background box if you are correcting your spectra. This is because you don't want to apply a correction factor to a baseline that's not your actual signal. So now we're ready to acquire our spectrum, so you want to click the apply button and then start acquiring the spectrum. After you click apply, you'll see a window pop up that has your spectrum. This yellow line is your spectrum filling up the screen as the monochromator scans through the different wavelengths. If you chose multiple scans, this will cycle through the wavelengths multiple times and it will add on the new counts onto the old counts. Note that the values here are negative because the dark signal has been subtracted from your main signal. When you're done, you can go to the File menu and then select Save. Be careful not to overwrite your files. It's really easy on this version of Windows because when you click on another file, instead of giving you the option to rename your file, it will automatically try to save your file as the same name. It will give you a warning, so it's important that you say no when it asks you whether you want to overwrite that file. You can also export your data by going to File, Export to ASCII, and this will produce a text file. In the next chapter, we'll talk about measuring lifetimes in MCS mode. First, we need to switch our infrared laser into pulsed mode, so we'll go back to our PM1 control box and flip the switch to pulsed mode. Previously, we had set this to CW. Next, we'll adjust the pulse width. So I like to start with a really long pulse, just because that way I know the system is getting as much power as it can. I can always reduce this pulse width later. Next, I'll open up the signal rate window, and then I'll set the emission bandwidth to 0.1 nanometers because I'm going to start changing the system and I want to protect the detector. In the source light path, I'll select the option that says MCS laser, and then I'll click apply. So this will change the counts. When you change your light path and your pulsing, your emission counts will go down just because your duty cycle is so much lower than in continuous wave mode. You want your signal to be as high as possible as long as it's less than 10 to the 4th counts per second, or about 5,000 counts above the noise level. You can adjust the emission slits to maximize your emission counts, and normally you would have to. In this case, you can actually increase the bandwidth pretty high because you don't really care about the resolution because you're not taking a spectrum. You just want to make sure that the bandwidth is about the same width as your emission peak width, or less. So once you're happy with your counts per second, you can click apply and then close the signal rate window. It's usually a good idea to acquire a steady state spectrum with your pulsed excitation before you run any lifetime measurement. This is because this will show you if there's enough signal to really get a good lifetime curve. Also, you want to make sure that there's not other peaks that are bleeding into your main emission peak. So once you've determined that your spectrum is okay and has enough signal for you to acquire a lifetime curve, then you can click on this tau button and select manual measurement. This will open up this manual measurement window along with the MCS measurement window. These two windows are normally stacked on top of each other at the side of your F980 window. So if we zoom in on the MCS measurement window, you want to change the time range to about 2 times your expected lifetime or greater. Then you want to choose the number of channels. Usually this is about 4096. This gives you the number of data points in your time trace. You can set the stop condition. A lot of people like to set the time as a stop condition, but you can also set the number of counts. Click apply, and then we're going to go back to our manual measurement window, and then click on the new or the triangle icon to start a lifetime run. So again, you can see we're going to click on the tau button, select manual measurement. And then in the MCS measurement window that opens up, we'll set the time range, the number of channels, and then the stop condition. We'll click Apply, and then in the manual measurement window, we'll click New to start a lifetime run. So we can see a black window opens up, and then you'll see all the time points accumulate counts over time. Hopefully you should see a decay curve that looks like this. Here you can see the laser pulse is turning on and the counts are increasing. And then after the laser pulse turns off, then you can see the counts decrease or decay. After the acquisition of the lifetime data is done, then you can analyze your data by going to the Analysis menu and then selecting Exponential Tail Fit. This should open up the Exponential Tail Fit window. First, you can set the time range for which you're fitting. Usually the automatic or default values are pretty good. It will automatically select the highest point as the start of your fitting range. Next, you're going to set guess values for the lifetimes. Usually I would select 2 to 3 so that I'm doing a double or a triple exponential fit. So then I can click Apply to do the fit, and it's usually very fast. So a second window will open up, and it'll show your curve cut off to the fitting range, and it'll also show a blue curve that shows the fit. Below these curves will be the residuals. You want to just make sure that there aren't very large residuals or ones that are not completely random. So in the same exponential tail fit window that you use for your guesses, you'll see now that those values have changed, and these are the fit parameters for your curve fit. So in this case, I have one exponential decay component that's about 260 microseconds, and then I'll have a second decay component that's about 1100 microseconds. So these B1 and B2 values are the amplitudes of these two lifetime components. So you can see here that the tau 1 or 260 microsecond decay is dominating. So again, you can see how these B1 components are related to the overall curve by looking at the equation. When you're happy with your lifetime fit, you can copy these fit parameters as text and then paste them into a text file. You can close the curve fit box, and then I would recommend saving the decay curve with the curve fit as a separate file. So that's measuring the lifetimes. You can see it's very simple in this software. Once we're done, we can shut down the instrument. We're going to turn off the lasers. Again, we normally want to turn the laser power down first before we turn off the laser. Then we're going to turn the key to off and then power off the power supply. We're going to flip the pulse switch back to CW mode, and then we're going to remove our samples from the sample holders. I also want to move the prism out of the light path just in case the next person wants to use the lamp. I'm going to use the rod to flip the prism counterclockwise until it bottoms out. In this case, the rod will be horizontal. Remember to remove any excitation or emission filters from the beam path. This is really important, again, in case the next person is trying to view a wavelength range that your filter is blocking out. Finally, you're going to power off the instrument. First, you want to turn off the CO1 power, and then you can turn off the pH1 power. Verify again that all of your light sources are off, including the lasers and the lamps. You're going to save all your data and exit the F980 application. Chapter 5, Troubleshooting. The Edinburgh spectrometer is pretty easy to use, but here's a few tips that will help you avoid common problems and increase the quality of your data. Always acquire a steady-state spectrum before a lifetime measurement. And when you're measuring lifetimes with the lasers, acquire an emission spectrum both in CW and pulsed mode to ensure that the triggering is functioning correctly. A common problem is that people will measure a spectrum and not see any signal. One of the solutions is to check that the prism is flipped into the beam path if you're using a laser, or check the prism to make sure it's flipped out of the beam path if you're using the lamps. Another problem is that the pulse spectra do not show any signal, even though the continuous wave spectra do. So here you want to make sure that the BNC trigger cable connections are correct. Remember, you want to unplug the microsecond flash lamp BNC cable if you're using the laser, and you do want to plug in a different BNC cable for triggering the lasers. Importantly, you're not going to snake the microsecond flash lamp triggering cable and put it onto the lasers. There's two separate cables and they should be labeled. If you observe a sharp decrease in the signal around 680 nanometers, or you see a bunch of sharp peaks in your visible range, then it's possible that your excitation source is bleeding into your emission spectrum. This could be due to scattering from your sample or just having a really dirty light source. So one solution is that you can install an emission filter that blocks out your excitation source, or you can install an excitation filter that can clean up your excitation source. So there are many other tricks to using the software and the hardware. We can't cover them all in this video. So if you have any other questions, ask a super user of this instrument. So today we showed you how to turn the system on, run a steady state emission experiment with the IR lasers, measure microsecond lifetimes using multi-channel scaling, and shutting down the instrument. And we also covered some troubleshooting tips. There's many other experiments you can run with this Edinburgh instrument. You can measure the spectra and microsecond lifetimes excited by xenon lamps. You can measure nanosecond lifetimes using the time-correlated single photon counting and the picosecond laser diodes. You can also measure spectroscopy and lifetimes using the near-infrared detector. We can measure quantum yields using an integrating sphere, and we can also perform high-throughput spectroscopy and lifetime measurements using a microplate reader attachment. So please contact a super user if you need to do these things, or check back on this channel for videos covering these different topics.